Hey, thank you very much for attending this webinar. Welcome to our sector webinar. The waste sector actually puts these on quarterly. So the title of our webinar is "Please Find a Solution." Landfill trends regarding regulation and treatment. Right. So "Please Find a Solution" is a very Jim Clunan derived name. So I'm not that clever. But I want to let you know that we have a pinch hitter today for Jim. Uh, Bill Malik is going to present in Jim's place. Bill is WSP Canada's water treatment lead, but like our entire PFAS team, we cross borders to address client challenges. As you can see from the summary bio up on the screen, Bill is one of the most credentialed PFAS treatment experts in the world. Before we begin, we thought that a PFAS focused safety moment would be appropriate. So I think, as all of you know, that PFAS are a class of thousands of chemicals that are often called forever chemicals. Many are toxic. They don't degrade easily. They're used in firefighting foams a lot, and that's how it's spread. They also have uses in industrial processes and within consumer products to impart their durability characteristics. They're readily transported through water, even through air. Some bioaccumulate. Simply put, they're bad news, at least for those that are toxic. In fact, PFAS is present at elevated levels in your blood, and actually in the blood of just about everyone on the planet. So to help keep PFAS out of our bodies, EPA has recently taken a lot of actions. And some of those are that they've added PFAS to MCLs, or several PFAS. And the ones they added were the most studied. So, they're shown here. The new rules require monitoring, consumer reporting and notification, and as needed treatment, to address any MCL exceedances. So, you know, with these going on now, you've wondered, like, well, how many people are actually impacted? So, as of April, the EPA has reported the UMCR. That's the survey that they're doing across all drinking water utilities to find out what's the extent of PFAS contamination. So what they've done in this latest tranche that they reported in April was that where they had enough data for annual averages, to be completed, so 2 or more for most facilities, some require quarterly if they're really big. Where they had those reports, or the sufficient number of reports over 1 year period, they compared it to that average to the MCLs, the new MCLs. So, based on that data, they're showing 10% have an exceedance, and we're going to need treatment. This number seems a little bit low to me, probably because there's a little bit of biasing in who supported, who put in their samples first. Probably a lot of cleaner utilities did that. Your previous UMCR data, the stuff that was released earlier in the year, before the April, suggested that about 25% of utilities would need treatment. Like they had at least a single hit of PFAS over the MCLs. So that's a quarter. That's a lot of us are probably, even a lot of us on this call are probably drinking water that has PFAS concentrations above the MCLs. So what can you do before 2029 to protect yourself and your family? That's I think a pretty good health and safety spot. The first thing to do is to check your purveyor's website for information on PFAS. If they confirm that there's PFAS is present, or even if you proactively want to make sure if they're not reporting it yet, you consider lowering your exposure by using point of entry or point of use treatment systems. WSP's put in thousands of these. These can get a little bit costly, so I don't think anyone would be running out to put these in. But unless you have a well that you want to make sure stays treated. But if you want to wait out the the regulatory time period, the implementation of the MCLs, then you can switch to bottled water for drinking and cooking. Even filtration pitchers have some benefits. Manufacturers responding to the market need, and uh, in providing in those pitchers, like the that you put in your refrigerator, treatment for PFAS. So, but be sure to read the labels on what it treats, because up until a few months ago, they weren't really providing much treatment. So, and please add any questions that you have on the health and safety moment into the Q&A. So we'll move on now that we completed the health and safety moment, and here's the agenda for today. Next up is we want to bring everyone's attention to a new landfill mass balance article. The graphical abstract is just the right on the slide. It was just published in Science of the Total Environment this past December, and the lead author, Thibet Telemat, and several other co-authors work for the EPA. So it may provide some insight into how the EPA is thinking about mass balances in landfills, PFAS mass balances. On the left of the image, it shows a total of about 7,500 or 1,000, kilograms of PFAS enter municipal solid waste landfills every year. And it quantifies the PFAS emissions through leachate and gas emissions. About 12,000 tons, 1,200 tons, are emitted annually. That's about 15% of the input. What jumped out at me with the emissions is how much of is emitted through the vapor phase versus through leachate. About 38% is through landfill gas collection systems and fugitive emissions. As you'll see in a few slides, in January, a month after this article came out, the EPA published OTM 50, which is an analytical method to measure PFAS and air emissions. I think you can kind of see the direction the EPA is heading here. And go here. So here we go with a PFAS 101. Just really quick catch up for some people who might not be as familiar with PFAS, but we're also going to dive in a little bit more into a little bit more complex issue or chemistry than you typically see in these things. So I'll fly through the 101 and linger a little bit on the 201. So we're all pretty experienced with traditional chemicals, right? That we encounter on an everyday basis. They're pretty black and white. Maybe there's a little bit of gray in there too. We know how to manage petroleum and chlorinated solvents and things that we encounter all the time. But in PFAS world, there are a lot more colors. According to Wikipedia, Crayola makes about 120 different colors. If Wikipedia says it, I believe it, but I swear there's more than that. But so this visual analogy is a bit limited when trying to show that there are thousands of PFAS. There we go. Their protective standards are a lot different than we're used to also, right? So they're much lower. Mercury is a contaminant I think most of us have bumped into. It's very toxic. It bioaccumulates just like many PFAS. Mercury has an EPA drinking water standard of 2 micrograms per liter, or 2 parts per billion. Let's draw a line that represents 2 parts per billion on the screen here. Okay, now let's take a look at the line for one of the most studied PFAS, PFOA. It has a drinking water lifetime health advisor of 4 parts per quadrillion. This is equivalent to a couple postage stamps on an area the size of California and Oregon. You can't see the line, right? That's not a PowerPoint mistake. We would need a microscope to see that line, and not just a visual light microscope like we all had in high school. We need an electron microscope to see the line. So the log scale chart that just popped up shows the health advisories and the new MCLs. Those are in red, the dots on the line, and you compare that to the green dot at Mercury at the very top. I used to think 2 parts per billion was a really low concentration, but I guess not anymore. So I'm not alone in thinking that it's kind of crazy low. Some prominent toxicologists from around the world think there are some serious flaws with the derivation of the health advisories. Often, some of them gathered in DC this past October to take a deep dive into exactly what went into the EPA's risk assessment process. WSP sponsored that and attended and presented at that workshop. I wasn't there. Toxicology isn't my wheelhouse, but some regulators were there, and the Alliance for Risk Assessment that they sponsored it, and the many professionals did participate in it. And they think they made a difference by pointing out the flaws in some of the EPA's methods. They right after this or soon after this, they came out with a re-examination of the nitrite risk. So that's a hopeful sign, but I think the issue is too politically charged to get back to following the science, but we'll see. So let's ramp it up a little bit and talk about what determines the physical characteristics and toxicity characteristics of PFAS. There are two primary differentiators that determine the physical characteristics. The first is the carbon chain length. These carbon fluorine chains are incredibly resistant to degradation. They impart durability characteristics. So they can vary 1 or 2 carbons all the way out to hundreds or thousands. So a subclass of PFAS that have really long fluorocarbon chains are the polymers. Here's an example of the basic Teflon structure shown at the bottom of the page, the monomers shown up at the top. The average Teflon fluorocarbon chain is over 1,000 carbons long. And there are many versions of this, and some versions are much heavier than this. They contain side chains, vertical extensions off the horizontal chain. Teflon on its own is relatively inert as long as it's at temperatures that are less than 400 or 500 degrees. But it gets a bad reputation from other PFAS that we use to help manufacture it, and chemicals and manufacturing aids that help apply it to consumer goods. Many of those contained other types of PFAS, the surfactants, that we'll talk about a little bit right now. The second determining characteristic has to do with the functional groups that are attached to the fluorocarbon chain. On the left is the 8-carbon perfluorinated chain. Again, the fluorocarbon chain can be of any length. But toxicologists have really focused on carbon lengths that are in the range of between C4 and C10. On the right are a few functional groups that can be attached to the fluorocarbon chain. This is nowhere near an exhaustive list. This is just some stuff that I thought of as I was pulling this together. You can see quickly, but by varying the length of the carbon chain and the functional groups, and the number of potential PFAS compounds is huge. So most literature citations indicate that there are thousands of PFAS, and that doesn't even include the polymetric PFAS. If you were to include those in the count, there'd be millions of PFAS. So here's an animation that shows how the structure of PFOS and PFOA are derived. Because these are acids, they have a negative charge. They're anionic at most pH values. PFO and PFAS, like I mentioned before, most studied PFAS that have been identified to date, and they have a part per quadrillion health advisories, as we talked about, and the 4 part per trillion MCLs. Their characteristics are similar to with relatively, their characteristics are similar to a lot of the PFAS that have relatively long carbon chains. Basically for the non-polymers. The anionic head. So the head is hydrophilic and the tail is hydrophobic. So they're surfactants. They're like soaps. You probably recognize the structure from like high school biology because it looks just like a phospholipid, right? Except it doesn't have hydrogens on there. Maybe you have carboxylates are used in there, or so it's very similar. So you can kind of see how phospholipids that are present in this animal cells it can include or incorporate some of these other surfactants. Um, so if we were to swap out the carboxylic in P4 or the sulfonic in PFOS with a neutral functional group like the fluorotelmer alcohol that's in the bottom there, um, this would totally change the physical characteristics of that substance. The fluorotelmer alcohols, PFAS, generally do not like to be in aqueous solutions. They like to partition to organic solids or into the vapor phase. So that's it for the chemistry. No more there. I know Bill's going to touch on some of the practical implications of the structures and physical characteristics a bit later when he talks about treatment. So let's get into the action drivers. You can tell the EPA's focus really by what they've published and what they've said. They've published a lot, starting with this roadmap here. I know you're all familiar with it. I'm not going to go through it. But what I want to bring up is that they are following through. Their timing might be delayed, but they are progressing with their agenda, and especially recently. They've established a track record. So in the next few slides, we'll dive into this a little bit. So we're going to try to keep the regulatory drivers grouped and focus on the waste industry, right? That's why we've gathered you here today, is to keep this focus. And of course, this is really a high-level summary. So let's start with the commerce restrictions, which should reduce the PFAS content of waste coming into landfills. This activity is being done through TSCA and state actions, and even actions through ECHA in Europe. There are a lot of activity progressing under TSCA that have been some research and new use limitations and other actions that I don't want to, I don't think all of you can care about that too much because it's not on the waste sector priority list. But one of the actions is focused on nearly all of our commercial industrial clients is the new PFAS reporting rule. Basically, it's a US-wide mass balance. Our commercial and industrial clients are scrambling to try to figure this one out, and where PFAS is present within their supply chain. And states are acting too in addition to on commerce restrictions, in addition to the EPA's trying to get a handle on what's going on in commerce. They're mostly focused on consumer products, and some of them even include total bans of PFAS. So this table here from saferstates.org, it shows 14 states that have some PFAS content restrictions in product sectors. These states are generally more aggressive in regulating PFAS in general. And here's a figure here that shows how aggressive different states are. Obviously we don't have a time to take a dive into each one, but generally the darker colored are more aggressive, the lighter covered are less aggressive with their state regulations, and probably going to be with their implementation of, or at least a little slower with their implementation of federal regs where they have primacy. So analytical methods, there's been some significant movement here, as mentioned in the safety moment, or actually just after the safety moment, we were talking about the landfill mass balance. As of January 2024, so this past January, method 1633 is final. It includes the measurement of 40 PFAS in non-potable water, soils, biosolids, landfill leachate, fish tissue, etc. It's an LC MSMS method, and it's been multi-lab validated and is ready to go. There's been a rapid transition from the modified drinking methods, 537.1 and 533 that have been used historically over the past few years to people switching over to 1633. Method 1621, determination of absorbable organic fluoride in aqueous matrix. That's a combustion ion chromatography method. It was also finalized in this past year. As I mentioned before, OTM 50, 30 PFAS in air. I think they're, there's the reason they got that out there. We look at that mass balance and some of the stuff they're doing in the power industry. So you be prepared for that, and put that on your radar that the EPA is likely to start upping their quantification or intense scrutiny of vapor emissions. And earlier this month, ASTM issued D 8560, which focuses on PFAS in indoor air. Safe Drinking Water Act, all right, we discussed that one pretty well in the safety moment. The one thing I'd like to add is that, you probably all realize this, but MCLs drive groundwater and soil cleanups in drive the derivation of the criteria in many, many states. So it's becoming real. Clean Water Act is a huge driver of PFAS activity. The EPA has lots going on there. The current status is in December 2022, the EPA took a really aggressive step by issuing guidance to encourage states to use their authority to require sampling to gather information and to set PFAS effluent limitations in NPDES permits. States are implementing based upon their own priorities and funding, but ultimately the data is going to going to land here. This is the EPA Echo database of PFAS analytical tools. It's a GIS. It's frequently updated with all sorts of EPA PFAS data. Waste facilities are already identified on here because they appear in EPA's PFAS handling industry database. So the draft, again, back to the Clean Water Act, moving down the graphic, it's draft recommended freshwater aquatic ambient quality criteria are out there, and I've seen some states are looking to be much more aggressive than the feds have been with these, and states receive fodder for their aggressiveness with the new RSLs that were just released. So they're going to be coupling the ecotoxicity with human health toxicity by food consumption, fish consumption, that sort of thing, and look for those criteria to be lowered quite a bit, and that's going to affect NPDES permits and discharges. In June, EPA, June 2015, the EPA published effluent guideline. It wasn't 2015; it was more recent than that. But anyhow, they published Plan 15. So within Plan 15, the EPA proposed or intends to revise or develop effluent limitation guidelines for several industries, including PFAS manufacturing facilities. That makes sense, and formulators of PFAS and processors. They also named chrome finishing industry as a target. They stated in Plan 15 that they intend to collect PFAS data on landfill leachate and revise the ELGs for landfills in the future. Other recent developments with the ELGs include updated ELGs for coal-fired power plants. The EPA is suggesting that states include PFAS monitoring and possibly best management practices in site-specific water discharge permits, right? So for those power plants, this marks the first time that the agency has addressed PFAS, even indirectly, in an ELG. And this past week, the OMB started to review on EPA's proposed PFAS ELGs for those chemical facilities that mentioned above that they had prioritized. So look for those to be coming in the next 60 to 90 days is what it usually takes OMB to spit out their economic impact information. And RECRA, so most of you already know about RECRA, probably a lot more than I do. So I'm going to keep this one going pretty fast. So in February, proposed rules were released. The first was to list 9 PFAS shown here as Appendix 8 hazardous constituents. The second was to clarify that Appendix 8 and 9 substances subject to RECRA investigation and corrective action. It also blended the statutory and regulatory hazardous waste definitions. It seems like they're trying to make it easier for them to add chemicals to the hazardous list. I need a lawyer to figure that one out fully, and a lot of you are probably ahead of me on that. So when the two proposed rules are finalized, the PFAS containing waste still aren't going to be hazardous waste, right? But they will be included in Appendix 8, and that's historically the on-deck circle, right? That's Bill's role for this call, to ultimately receiving hazardous waste designations. The EPA and its delegated states would be able to require investigation and corrective actions for PFAS at hazardous waste treatment, storage, and disposal facilities once it's finalized. A couple open questions that I have here that maybe in the chat you guys can fill me in is would this only be applicable to current RCRA facilities? The PFAS applications, they're going to have to just existing. What about all the closed facilities that are out there? There is this a potential reopener, and will facilities that handle and treat PFAS alone, or it be required to obtain RCRA permits? And last in the regulatory update is CERCLA. So, they finally did it. They listed PFOA and PFOS as hazardous substances. They didn't go for the full list that they had announced earlier, but this is still pretty substantial. So when the PFAS listed under CERCLA goes live, and that's on July 8th, the regs or the new rules go live just in a few days. It's going to mark the first time the EPA has designated hazardous substances under CERCLA. CERCLA has substances have usually been designated by reference. For example, by any PFAS that is designated as hazardous waste under RCRA, they would automatically become hazardous substances under CERCLA. Other provisions of CERCLA will be applicable to PFAS that are designated as substances, including so that's PFO and PFOS. Reporting, like release reporting. So within default 1 pound release within the 24-hour period, and I ran the numbers on this for what it would take, how many gallons of C8 firefighting foam, and it doesn't take much to qualify as a reporting relief or to trigger the reporting relief requirement. It's a couple hundred gallons, and that's as mixed as the 1 to 3% mixture. So the EPA can also hold responsible for releases and responsibility through CERCLA's strict and joint several liability scheme, to recover costs. We all know how much that bites. These listed PFAS will be considered hazardous ranking lists for determining whether or not it makes the fund, makes CERC list. And you expect a whole bunch of new 104E letters to go out, even for existing new OUs and existing Superfund sites. Yeah, so it's a lot going on there. But in the same day that EPA issued the new CERCLA rule, they also announced enforcement discretion that basically provides relief to publicly owned entities like municipal landfills and airports. There's a full list up on the screen here. So we've just knocked that out. That wraps up the regulatory discussion. Let's run into investigation trends. And with the investigation trends, when Jim and I were pulling this together, we had big plans to take some deep dives here, but as we started building slides, we quickly realized that we're not going to be able to fit everything in, or at least everything that we want to within an hour time slot. So we've scaled it back a little bit, but I still wanted to provide a little information on some trends, but also stay within our time limit. So from the PFAS 101 and 102, you probably on your own experience, you've realized that PFAS are a little bit different than most contaminants we've become accustomed to. So I wanted to quickly share some of the differences that I think are the most consequential. And maybe down the road we can take a deeper dive, focus for another webinar on fate and transport, because it could easily fill up an hour just talking about fate and transport of PFAS. So most PFAS plumes have dark matter associated with it. So by dark matter, I mean it's not on the target analyte list for 1633. So there's thousands of these things, and 1633 only quantifies 40 of them. One class of the dark matter, or precursors, they can actually transform into the light matter through oxidative process. So the TOPA analysis, total oxidizer precursors, that shines a light into this dark matter. So that's an important thing to remember, because it could save you some confounding situations trying to figure things out and what's going on with mass transport, knowing how much dark matter is present, especially those that are oxidizable into light matter. Retention. So I think of retention as natural attenuation mechanisms, except for destruction. Which doesn't really happen, or at least not significantly. It doesn't happen naturally. So like all physiochemical traits, it's important to remember that retention characteristics will vary based upon the structure of the particular PFAS being evaluated. But in general, PFAS lake surfaces, and maybe even in many form micelles, if their concentrations are high enough, that can be a confounding deal. Some like to petition to most like to petition to the soil and sorb phase. And as we discussed earlier, some like to petition into the vapor phase. Anti-exchange capacity is an important fate and transport, especially for the PFAS, the alkyl acids. And salting out, that's something that people might not have heard about, but it's also a retention mechanism that slows the fate of PFAS transport. Salinity, or the polarity of the water, increases less polar PFAS sorption, so to the saturated soils. So you can even get some of the more soluble PFAS wanting to get away from all that polar solvent and onto the hydrophobic soils. And finally, PFAS, in the PFAS world, back diffusion, it isn't really a bad thing. It can do peak shaving. So it can, in effect, slow transport and even out or lower the concentrations that are measured. So those are just a few things that I observed in fate and transport. Sorry to run through those so quickly, but it's next time we'll do it. So that wraps up my portion of the talk, and let's get to what's pertinent to most waste consultants now, the treatment, and where we stand with technology right now on treatment at landfill. So Bill, please take it away.
Thanks, Matt. All right, if you can just advance the slides. All right, like Matt said, want to kind of take a look at some treatment approaches. I think the case study in landfills here in 2021, EPA found 95% of landfill leachates contain PFAS. Consumer goods, other materials that are going into the landfills. Keep moving through this, Matt. That leachate, leachate's typically discharged to POTWs under pre-treatment agreements. That then causes problems because POTWs have difficulty in managing their biosolids because the biosolids do partition into the biosolids and stay, some stay in the liquid stream. So landfills are looking at on-site treatment, deep well injection, hauling, and there's a big cost to that. And this is, median PFAS in landfill leachate is pretty high when you look at, what the 4 nanogram per liter concentration targets are. So, next slide. So when we talk about treatment, I think one of the big things that we've got to look at is we've got to look at the nature of the PFAS that we're dealing with. And so PFAS is longer chains are more amenable to treatment, especially when you're talking about treatment using foam fractionation, treatment using adsorption processes. So longer chains tend to be more treatable using those treatment methods. Also, the functional groups are important in that, the carboxylic acid functional groups tend to be less adsorbable when it comes to treatment using adsorption activated carbon ion exchange. And you get into the the C4s, the PFBAs, a lot more soluble, a lot harder to remove using foam fractionation or adsorption. They tend to zorb, but then desorb. And we'll talk a little bit more about that. And then even to get into fluorotellumer alcohols, where you've got volatility that gets introduced. So next slide, Matt. So you got to understand what you're dealing with, and I think that the key thing is that there's not one size fits all. There's not one treatment system that can be considered the best treatment system. Treatment systems vary in their applicability. The matrix that you're dealing with, co-contaminants that you're dealing with, those are all very important. And understanding what you've got in terms of a PFAS matrix, but also a co-contaminant matrix. Organic co-contaminants, aren't gonna deal well maybe with a granular activated carbon if you're going to get a lot of biofouling, or an ion exchange media. Really impacted by inorganic iron, for instance, can create a lot of problems. So you really need to know what you're dealing with, and then understand the chemistry and how that chemistry reacts. You're dealing with PFBA. It's got a low Henry's law constant, and you get into the 6,2 FDOH, much higher. So it's going to partition into the vapor phase more readily. Next slide, Matt. So planning the attack. Know that carbon fluorine bond is very difficult to break. It can be broken, but it takes a lot of effort to get there. Where the material winds up. I mean, we're seeing, as Matt said, we're seeing PFAS compounds globally in areas that you wouldn't expect to see them, or certainly wouldn't expect to see other contaminants. The chain length we've touched on, and then the co-contaminants playing a significant role. So even when you get into like the Gen X shown at the bottom there, where you might expect that you're going to have a weak link within it, it's still not particularly degradable, right? It's not an easy attack point, and there really aren't easy attack points in the structure. We know the persistence of PFAS in groundwater, highly mobile. It does absorb to soils, but then it also desorbs, and so you get this high mobility. You get transformations that occur in the groundwater as your redox potential changes within the groundwater systems. So just to touch on some updated EPA guidance on treatment and disposal options. So we'll just go to the next slide, Matt. So the main takeaways of the EPA guidance, there's really limited destruction technologies available, at least commercially available right now. The strength of that carbon fluorine bond requires high temperatures when we're looking at thermal treatment systems, higher than what you would typically use maybe for carbon regeneration. You have to get longer retention times, higher temperatures, and there's still the jury's still out on the products of incomplete combustion and whether the full fluorine mass balance is understood within the thermal treatment systems. And then you get into transformations where you might get hydrofluoric acid present, and that causes a whole host of other issues. And then when it comes to disposal, there's limited disposal because that disposal is limited to underground injection or into specific landfills. So, and Matt already touched on sort of the fate of PFAS in landfills and where it can partition. Next, Matt. So this is a simplified landfill disposal decision tree that was published by the EPA. It gives an idea. I think you really want to look at your decision tree with more rigor and make sure that you're not maybe necessarily following this blindly, that you've taken all parts of your systems into consideration. Next. As far as injection wells go, class 1 non-haz industrial waste facilities can receive PFAS material, but again, you're limited on where those facilities are. Not all states have them, and the cost of those is pretty significant. There are currently new wells being permitted, but ultimately the transportation and use of those is key. When it comes to treatment, there isn't a best treatment approach. Again, I talked about that treatment approach is really got to be site specific, material specific. We're dealing with liquid train treatment systems or solid train treatment systems. We're pretty limited on what we've got. Right now we're concentrating PFAS primarily. We're either concentrating it onto an adsorbent or exchange media, or through foam fractionation or a membrane system. We can take that concentrated PFAS, treat it thermally. There are some chemical treatments out there, but again, limited use with those and pretty high cost. Just going to cover a few, treatment processes. So the first one is membrane treatment systems. You've got a rejection of the PFAS compounds with RO, primarily reverse osmosis, nanofiltration. You can use some amendments with nanofiltration to reject the PFAS. The key thing to keep in mind is that with a landfill leachate, you're probably not going to be able to get to a high rejection rate. Or high recovery rate on the membrane system. So you're going to be creating a fair volume of reject. And so you have to keep that in mind when it comes to looking at a membrane system, because with leachate, you're probably not going to get up into the 90% recovery on water. So you're 99% rejection of the PFAS, but the volume of water that you're producing is not insignificant and has to be dealt with. Next. Foam fractionation, I personally think foam fractionation has a great deal of applicability with landfill leachate. The functional groups on longer chain PFAS have them acting as like surfactants, so they create foams when you introduce air into them. That foamate can then be treated thermally, chemical oxidation, other means, because you've really reduced the volume. We're talking about orders of magnitude in volume reduction that you're able to achieve with foam fractionation. And it's usually in a multi-stage kind of almost like a distillation sort of setup, where you're kind of taking one phase and then refoaming that foamate material. The water phase has much significantly reduced PFAS concentrations. Maybe allowing you to reduce or eliminate further treatment downstream, or at least significantly reduce the amount of material that's being used. And we're aware of some folks who are doing these systems. They tend to work pretty well with longer chain PFAS compounds. I know there's a lot of work being done to try and improve the foam fractionation performance on shorter chains with the different additives. So next slide, Matt. And this is just kind of looking at that, where we're, the highest operating cost is potentially the reagents, where you're adding co-surfactants to enhance the foaming and the removable on these systems. And again, you get real good long chain removal, and then that removal drops off as your chains shorten, and pretty low removal when you get down into the C3s and C4s or lower anyway. Next. When it comes to destruction, right now, really limited. As I mentioned, you've got incineration. There's some vendor applications out there. They're looking at, electrochemical oxidation. I'm involved in some liquid EO systems, supercritical water oxidation or SQO, liquids and solids, and plasma systems. Under development, there's a lot of stuff under development. I think there's some promising technologies out there, but we're still working on some of the developments there. I know, personally have some work being done on pyrolysis and gasification, and we're seeing some really promising results, just not there yet in terms of being able to say that it's field implemented. Next. A lot of talk about supercritical water oxidation, and it is, demonstrated. It is able to destroy the PFAS compounds, and supercritical water oxidation has been around for a long time. The knock on it's always been sort of the specialty metallurgy that's required for it, because it kind of oxidizes everything, including the metal that it's built from. So you're dealing with some pretty unique materials. However, we've got a number of vendors out there who have got systems that are commercially available for this. They're applying it, quite expensive, but it does give a route for small volumes right now. Those volumes are increasing. Next. Hydrothermal alkaline treatment again. This is something that's meant for high strength PFAS, such as foamates, RO rejects, possibly spent GAC and IX resins. It's been developed at the bench scale with greater than 90% destruction, and they're trying to increase the size of the systems. Next. So electrooxidation. So this is primarily a water treatment technology where you're using a voltage applied to a system to create an oxidizing condition, and that destroys the PFAS in the bulk water. So next slide, Matt. And with this, we've seen excellent results both on the bench scale, and we're moving to full scale on this. Some of one of the knocks on it is the potential generation of perchlorates. So there's a lot of work being done in that area to try and minimize the chlorate formation. But good removals. Again, short chains, not as well treated as longer chains. Next. And kind of the tried and true is really the absorption technologies, the granular activated carbon, anion ion exchange, and organoclay materials. Have found good applicability with this. Different systems, maybe you're using multi-adsorbent systems. We've used organoclay, GAC, and ion exchange in one train, depending on the water, and kind of talking about that water characteristic with co-contaminants and whatnot. Next. And this just gives an idea of what happens with some of the short chains in granular activated carbon systems. And the blue line there is PFBA. And as you can see, PFBA gets removed in the carbon systems, but then actually starts to release as the sites in the carbon get taken up. And it releases until that kind of comes back down to the inequally out on the PFBA. So next. And similar sort of thing happens with ion exchange. The breakthrough is a function of the chain length and also the functional groups, but you do see the same sort of effects. Next. Ball milling is an interesting technology that's has good potential for soil management. It's a well-known technology, and basically it's using high velocity impacts from steel ball bearings and a sand matrix to mechanically destroy the PFAS through impact. And it's had some good bench scale success. Again, bench scale does not always translate to field applicability, but it looks promising for sure. So in summary, GAC and ion exchange typically are the go-to. SQO and other treatment technologies are going to find applicability. It's just finding the right home for them, finding the right application for them. The destruction technologies can take up a lot of energy, maybe creating greenhouse gas emissions if you're talking about thermal destruction. And so how do we combat that? Again, that's kind of a innovation is part of this. Looking at low energy destruction technologies, or technologies that maybe produce energy. SQO claims that they can produce energy from their systems if they scale them high enough, or beneficial reuse of those destruction products. Biochar, syngas. If we can get to pyrolysis being effective, we can generate syngas from the organics that are broken up, and then potentially use that to heat the system. And then ultimately in situ PFAS control technologies, whether that's Rembind or others that are used to either immobilize or treat. So I think that's kind of the end of mine. Matt, you want to take this from here? You're muted, Matt.
Sorry about that. I was saying some really great things. So I think we did a decent job of covering these. Obviously went through very quickly, but in the hour time frame. As you can tell, Bill knows that he's an expert in all these. He's teed up to be the agnostic advisor. So if you have any questions on treatment, please reach out to Bill. So I think the takeaways are that we're still getting there, right? There's still a lot of work to be done on the research side. There's a few things that are out there on the that are being field implemented, and there's a bunch of research that thinks they're ready to be field implemented. They're just looking for the right sites. So stay tuned. We expect the technologies to rapidly expand, but then again, as Bill mentioned, they're going to have certain niches where they work best. So lining up the right waste stream with the right technologies is going to be key. So I guess if we had to predict the future here, a couple of little things that I think we threw together. There's going to be some challenges to the MCLs. We've heard a little bit, but I'm that 2029 might not hold. The draft ambient water quality criteria are going to probably end up in the PPT range, right? So that's going to require a lot more treatment and a lot more innovation to deal with all the volume of water. You think about how much gets discharged to aquatics and even like stormwater, and how can we tackle this stuff at these low ranges. More vendors are going to offer turnkey solutions, especially around leachate treatment. But you got to be careful, because most vendors sell one thing, right? And not there's no one perfect technology right now. So keep your heads up and realize what the sweet spot is for each technology where vendors come in. So I look at this as the same as vendors that are applying or have different in situ amendments. Like there's now a gazillion of those, right? But each of them has IP that put them in a band where they're useful in the right circumstances. So be looking for those applicability bands. Recycling, could take a bit of a hit. Not quite sure how this is going to lead, but the use of manufacturing aids and foam mold releases and extrusion aids have put PFAS into lots of plastics. So we'll see where that lands. but there might be a big impact on recycling. And testing and labeling of food products, we see this one coming up really quickly, especially when you combine PFAS with the microplastics that are becoming emerging more and more as an emerging contaminant. So that's us putting our guru hats on here. So, like PFAS provide a lot of benefits, so we can't lose sight of that. So, and this comes back to a lot of the commerce regulations, where some states like Maine, Minnesota, and Washington have total bans in place, or enacting total bans that are going to phase in over the next 5 or 6 years. They're prepared to add necessary use exemptions. But they're starting out with the universe of PFAS, especially as we talked, like a lot of these are inherently not very toxic, like the big polymers. They provide huge benefits. And I was talking with Bill, and just think about one thing alone, like, if you get rid of Teflon O-rings, right? Think of how much fugitive emissions there would be. Teflon has its place. So we need to take a balanced approach. And with that, if you don't have the time to type questions, and now you drop an email or give a Bill or I a call. So we're happy to continue the conversation. Well, thank you all for your time. We appreciate it.